When the US military needed a warship to push through the Strait of Hormuz, the most heavily armed and mined waterway on the planet, they didn't send a carrier or a destroyer. They sent a 3,000-ton aluminum ship with a documented history of cracking hulls, catastrophic propulsion failures, and a congressional record full of politicians calling it a waste of money. This is the truth behind why the US Navy chose its most broken ship for the hardest mission. But before we get started, make sure to hit that subscribe button and let's get into it. Chapter 1. The cage Iran built around the strait. To understand why this ship was chosen, you have to start with the map, because the decision didn't come from a boardroom. It came from geography. The Strait of Hormuz is 21 nautical miles wide at its narrowest point, but the usable shipping lanes compress down to just 4 nautical miles, 2 in each direction. 20% of the world's crude oil moves through that corridor every single day, and Iran has spent 40 years turning it into a kill zone. Here's what that actually looks like. Beneath the surface, thousands of naval mines are scattered across the seafloor. Contact mines, bottom influence mines, and EM-52 rocket-propelled mines that sit dormant until a ship passes overhead and then launch upward. Behind those mines, more than 20 Ghadir-class submarines lurk in the acoustic clutter of the shallows, carrying torpedoes and additional mines. On the surface, over 1,500 IRGC fast attack craft, small fiberglass hulls capable of 50 knots, many armed with the Nasser-1 anti-ship missile. They don't fight in formation, they swarm. Their doctrine is saturation, enough mass arriving at once to overwhelm any defense system's ability to respond. But it doesn't stop there. From the air, drone swarms flood radar screens with hundreds of low-speed signals, forcing air defense computers to burn through processing cycles, sorting real threats from noise. And hidden behind all of that electronic clutter, IRGC ballistic missiles descend at Mach 3. The cheap decoys are the distraction. The missiles are the payload. This isn't random aggression. It's a precisely engineered anti-access system built around one specific physical constraint. The time it takes any modern combat system to detect a threat, classify it, get authorization, and fire an interceptor is longer than the flight time of a weapon launched at close range inside those confined waters. Iran didn't build this to win a fair fight. They built it to make the fight unfair before it starts. So what does that constraint actually lock out? Everything big, everything expensive, everything that takes too long to maneuver in a bathtub. Chapter 2. Why the best ships can't go. A Nimitz-class carrier displaces 100,000 long tons. It carries 5,000 sailors and costs roughly $15 million a day to operate. You don't push that into 4 miles of mined water, where the enemy has had 4 decades to rig every square foot. The carrier's radar and thermal signature alone make it the highest priority target in the region. Its draft is too deep for the shallows. Its turning radius is too wide for the corridor. And if Iran's ballistic missiles find it, you're not just losing a ship. You're losing a fifth of the Navy's strike capability in a single hit. Destroyers and cruisers face a different problem. They're more agile, and their Aegis combat systems are the most capable naval air defense ever built. But their vertical launch cells are loaded with SM-6 interceptors and Tomahawk cruise missiles, assets critical to the broader operation. You can't afford to park those inside a dense minefield where a single pressure mine ends the equation. And destroyers aren't designed for mine countermeasures. That's a completely separate mission set. Submarines can't launch drones from a submerged position. That eliminates them for the offensive role entirely. So what does CENTCOM actually need inside that cage? 2 things, running simultaneously. An offensive platform that can get close to the Iranian coastline and launch cheap attack drones into the radar net, saturating the interceptor grid and opening corridors for the Tomahawks behind it. And a defensive platform that can deploy unmanned systems to hunt and neutralize mines without sending a single sailor into the water. The platform needs a small radar footprint, speed above 40 knots to deny targeting solutions, a large stable deck for drone operations, and a shallow enough draft to go where nothing else can follow. Run those variables against every hull in the US fleet. Only one answer comes back. Chapter 3. The ship that everyone wanted to throw away, the Littoral Combat Ship, LCS. The program that Congress called a waste of money, that the media called Pentagon's floating garbage, and that the Navy's own leadership very nearly killed entirely. There were two variants, and both had serious problems. The Freedom class was built around a propulsion system that channeled two diesel engines and two gas turbines through a single combining gearbox. The torque loads exceeded what the gear teeth could sustain. They ground themselves into metal dust while the ship was still underway. USS Milwaukee, LCS-5, lost all propulsion 1 month after delivery on her very first voyage. USS Detroit, LCS-7, went completely dead in the water and had to be towed back to port. Admiral Mike Gilday, the chief of naval operations, called the combining gear failure the most challenging engineering problem he'd seen on any ship class in his entire career. The Independence class had a different failure. A trimaran hull built entirely from aluminum. 3 narrow hulls connected by a wide upper deck. Aluminum saves weight and weight saves speed, but aluminum fatigues under the relentless cyclic stress of ocean waves. Structural cracks propagated through high-load junctions. The Navy was watching its warships tear themselves apart from the inside. Several were decommissioned before they'd reached even half their intended service life. Ships that never grew old enough to fight. So why is this the ship CENTCOM handed the most dangerous mission in the Gulf? The answer isn't inside the ship, it's in what the failures accidentally left behind. Chapter 4. How the defects became the features. Here's where the engineering gets interesting. Because the two biggest failures of the LCS program didn't just survive, they produced, without anyone planning it, exactly what the mission required. Start with the cracked hull. The trimaran design that was tearing itself apart under ocean stress also created something a conventional monohull never could. 3 hulls spread wide apart generate a significantly larger metacentric height, which is the distance between a ship's center of gravity and its center of buoyancy. That measurement directly controls how violently a ship rolls. Think about the difference between standing in a canoe versus standing on a wide catamaran. The wider the stance, the harder it is to tip. The Independence class, because of its 3-hull geometry, stays remarkably flat even in open ocean swells. For a traditional warship firing guns or missiles, that's not especially important. But for a platform launching rocket-assisted drones from a flight deck in the middle of the Arabian Sea, it's everything. A rolling deck produces inconsistent launch conditions. An unstable platform produces unreliable weapons. The trimaran's structural weakness created, as a byproduct, the most stable drone launch platform in the entire fleet. Now consider the modularity failure. The LCS was originally designed around swappable mission packages, anti-submarine warfare modules, surface warfare modules, mine countermeasures packages that could be loaded and unloaded in port depending on the mission. The concept failed completely. The modules were late, over budget, and underperforming. The Navy eventually abandoned the whole plug-and-play vision. But when you pull the failed modules out, what's left? Over 11,000 square feet of open, unobstructed flight deck, roughly the footprint of 3 tennis courts. That empty space wasn't designed as a feature. It was left behind by failure. And it turned the LCS into something nobody planned for, the most flexible launch platform in the fleet. Bolt a rocket-assisted drone launcher onto it. No structural modification needed. The ship doesn't need to be good at everything. It just needs to float, move fast, and open that deck to whatever the mission demands. The cracked hull became the stable table. The failed modules became the open garage. And the low unit cost, the same cost that made Congress furious, became the acceptable risk that let CENTCOM push LCS into the one place no other hull could go. Chapter 5. The $35,000 weapon that broke Iran's air defense. So what do you actually put on that deck? In December 2025, USS Santa Barbara, LCS-32, was operating in the Arabian Gulf when a rocket booster fired from her flight deck and a small delta-wing aircraft climbed into the sky. 10 feet long, 8-foot wingspan. That was the first shipboard launch of Lucas, the low-cost unmanned combat attack system. The first time the U.S. Navy had ever fired a one-way attack drone from a warship at sea. 2 months later, that weapon went to war. Here's what makes Lucas extraordinary. Its airframe was reverse-engineered from Iran's own Shahed 136, one of the most battle-proven one-way attack drones in modern warfare. Engineers at Spectre Works in Arizona studied exactly what made it effective, kept the aerodynamics and low-cost manufacturing approach, and rebuilt everything else. Then they flew it back to the country that designed the original. But Lucas isn't a copy. 3 specific upgrades separated it from the weapon it was modeled on. First, propulsion. The Shahed runs a crude 4-cylinder engine that broadcasts its acoustic signature across the water. You can hear it coming. Spectre Works replaced it with a DA215 two-stroke engine with electronic fuel injection. The noise reduction is significant enough that radar detection, not sound, becomes the primary warning system Iran has to work with. Second, guidance. The Shahed follows pre-programmed GPS coordinates. Fire and forget. Lucas maintains a live uplink through the Starlink satellite constellation, solving the radar horizon problem, the physical limit where Earth's curvature blocks line-of-sight targeting. Through Starlink, an operator can redirect a Lucas against a moving target completely beyond visual range, with a human making the final decision before impact. Third, and this is what makes a swarm genuinely devastating, Lucas carries autonomous coordination algorithms. Drones in a formation communicate with each other, sharing trajectory data, allocating targets, and coordinating approach angles. A single Lucas is a nuisance. 20 Lucas, drones arriving simultaneously from different directions, is a computational crisis for any air defense network. Now run the cost math. Each Lucas costs $35,000. The SM-6 interceptor Iran would fire to destroy it costs nearly $5 million. Iran spent 40 years engineering a system designed to drain American interceptor magazines. Lucas inverted that math entirely. When Epic Fury commenced, Lucas drones launched from LCS flight decks and struck IRGC command nodes, early warning radar installations, missile launch sites, and military airfields. CENTCOM Commander Admiral Brad Cooper called Lucas indispensable, not useful, not helpful, indispensable. And once those drones saturated Iran's radar grid and exhausted its interceptor supply, the Arleigh Burke destroyers behind the LCS opened their vertical launch cells. Tomahawks, $2 million each, flew through the corridors Lucas had torn open. The expendable drone doesn't kill the hardened target. It blinds the defense that protects it. The Tomahawk finishes the job. For the first time in history, the U.S. Navy synchronized cheap attack drones with strategic cruise missiles inside a single kill chain in actual combat. Chapter 6. The Minefield. Nobody had to enter. While Lucas was tearing holes in Iran's air defense overhead, a second mission was running in the waters below. Because controlling the strait isn't only about destroying threats, it's about clearing a path. USS Canberra, LCS-30, arrived at Naval Support Activity Bahrain in May 2025 as the first Independence-class LCS to deploy with the full mine countermeasures package. USS Tulsa, LCS-16, and USS Santa Barbara followed. 3 platforms, each carrying layered unmanned systems built around one core principle. The ship stays outside the threat zone. The robots go in. The Common Unmanned Surface Vehicle is a remotely controlled boat that tows the AQS-20 mine-hunting sonar through suspected mine zones. The sonar builds a detailed picture of the seafloor, identifying objects by shape, density, and magnetic signature. The human operator sits on the LCS miles away, watching the data feed. Nothing in the water. Nobody at risk. From above, MH-60S Seahawk helicopters add 2 more detection layers. The airborne laser mine detection system scans the water column with a blue-green laser, finding floating and near-surface moored mines that bottom sonar can't reach. Once a mine is confirmed, the airborne mine neutralization system deploys a small unmanned underwater vehicle that swims directly to the mine and destroys it. 3 detection layers, 3 unmanned systems, 0 sailors in the water. The previous mine-clearing platform, the Avenger-class minesweeper, required its crew to operate directly inside the minefield. The last 4 Avengers were withdrawn from Bahrain in September 2025. LCS didn't just replace them, it removed the human from the danger entirely. Chapter 7. What happened when both missions ran at once? Now watch what happens when you combine them. 2 missions, same class of ship, running in parallel on the same battlefield simultaneously. On the offensive side, LCS platforms pushed through the Gulf at over 40 knots, constantly shifting position, never holding still long enough for Iran's coastal batteries to lock a targeting solution. From those moving decks, Lucas swarms launched into Iranian airspace, dozens of drones flooding radar screens. Every interceptor Iran fired at a Lucas was one fewer available when the Tomahawks arrived. The air defense grid burned through its finite magazine, engaging $35,000 targets. Then the destroyers opened their cells and precision flew through the gap. On the defensive side, other LCS platforms deployed unmanned surface vehicles and helicopter-borne systems into the mined waters of the strait simultaneously. Sonar mapping the seafloor, lasers scanning the water column, robot swimmers neutralizing what they found. The corridor Iran had seeded with thousands of mines was being cleared by machines while the air war ran overhead. The results wrote themselves across the surface of the Persian Gulf. Iran's Jamaran, a Muj-class frigate and one of Iran's most capable surface combatants, was struck and sunk at Bandar Abbas Naval Base. CENTCOM released satellite imagery showing the hull partially submerged at the pier. 2 corvettes, the Bayandor and the Nagdi, were destroyed at the same base. 3 Iranian warships that never made it out of port. And then there's the detail that tells the whole story. The Shahid Bagheri, a commercial cargo vessel the IRGC had spent years converting into a makeshift drone carrier by welding an angled flight deck onto a freighter hull, was destroyed at her berth. Iran's answer to drone warfare at sea, built from scratch over years, never sailed into combat. It was broken at the pier where it was born. Now look at what launched the drones that helped destroy it. A 3,000-ton ship with cracking aluminum skin that our own Congress called a waste of money. Iran built a drone carrier from scratch and lost it. The US took a ship everyone wanted to scrap and turned it into one that worked. That's not irony, that's engineering. Over the course of epic fury, more than 100 Iranian naval vessels were destroyed. The surface fleet that was supposed to swarm and overwhelm US forces in the shallow waters of the Gulf ceased to exist as a fighting force. Now you have the data. Go back to the question we started with, and this time you already know the answer. Why the worst ship? Why LCS? Because the equation didn't ask for the best ship, it asked for the right one, small enough to enter the cage, fast enough to survive inside it, a deck wide enough and stable enough to launch drones, cheap enough that losing one doesn't break the fleet. Run those 4 variables against every hull the US Navy owns, and only one answer comes back. The engineers didn't fix the cracked hull. They didn't repair the failed modules. They ran the equation again and the failures became the features. The empty deck that modularity left behind became a drone launch pad. The trimaran hull that cracked under ocean stress provided the stability that rocket-assisted launch demands. The low cost that embarrassed the program became the risk tolerance that let CENTCOM push LCS into the one place nothing else could operate. What LCS proved isn't just about one ship or one operation. It's a principle that's going to define how naval warfare is fought for the next generation. You don't need one platform that does everything. You need many platforms that each do one thing, connected by a network that multiplies their effect. Distributed lethality isn't a PowerPoint concept anymore. It's a doctrine tested in combat and validated by a ship that was never supposed to see any. The future of naval power doesn't belong to perfect machines. It belongs to imperfect ones, in the right position, running the right equation. LCS was never a good ship. It was the right variable, and the equation worked. If you enjoyed this video, make sure to hit that subscribe button, and we'll see you in the next one.